Belief propagation. Having discussed some inference examples by hand, we now are interested in an algorithm that can answer queries such as P of x conditional E, where x is any query node in the graph and E is any subset of evidence nodes whose values are set to certain value. Following Pearl in 1988, we started with the simplest case of chains and gradually move on to more complex graphs. Our aim is to find the graph operation counterparts of probabilistic procedures such as Bayes' rule or marginalization, so that the task of inference can be mapped to general-purpose graph algorithms. Chains. A chain is a sequence of head-to-tail nodes with one root node without any parent. All other nodes have exactly one parent node, and all nodes except the very last leaf have a single child. If evidence in the ancestors of X, if the evidence is in the ancestors of X, we can just do a diagnostic inference and propagate evidence down the chain. If evidence is in the descendants of X, we can do a casual inference and propagate upwards using Bayes' rule. Let us see the general case where we have evidence in both directions, up the chain E plus and down the chain E minus. See figure 16.11. Note that any evidence node separates X from the nodes on the chain on the other side of the evidence, and their values do not affect P of X. This is true in both directions. We consider each node as a processor that receives messages from its neighbors and passes it along after some local calculation. Each node X locally calculates and stores two values. Lambda of X is defined as the probability of E inverse condition E minus conditional X is the propagated E minus that X receives from its child and forwards to its parent, and the pi of X is defined as the P of X conditional E plus is the propagated E plus that X receives from its parent and passes on to its child. Now P of X conditional E is equals to P of E conditional X times P of X divided by P of E, which is equals to P of E plus and E minus conditional X times P of X divided by P of E, which is equals to P of E plus conditional X times P of E minus conditional X times P of X divided by P of E, which is equals to P of X conditioning on E plus times P of E plus times P of E minus conditional X times P of X divided by P of X times P of E. That is equals to alpha times P of X conditional E plus times P of E minus conditional X, which is equals to alpha times pi of X times lambda of X for some normalizing constant alpha, not dependent on the value of X. The second line is there because E plus and E minus are independent given X, and the third line is due to Bayes' rule. If a node E is instantiated to a certain value, that is E wave, then lambda of E wave is divided by 1 and lambda of E is equals to divided as 0 for all those E, which is not equals to E wave. The leaf node X that is not instantiated has its lambda of X defined by 1 for all X values. The root node X that is not instantiated takes the prior probabilities as pi values. That is, pi of X is defined by P of X for all X. Given these initial conditions, we can devise recursive formulas to propagate evidence along the chain. For the pi messages, we have pi of X is defined as P of X conditional E plus, which is equals to sigma summing for all U of p of x conditional u and e plus times p of u conditional e plus, which is equal to sigma summing for u of p of x conditional u times p of u conditional e plus, which is equal to sigma summing for u of p of x conditional u times pi of u, where the second line follows from the fact that u blocks the path between x and e plus. So for the lambda messages, we have that pi of x is defined as p of e minus conditional x, which is equal to sigma summing for oy of p of e minus conditional xy times p of y conditional x, which is equal to sigma summing for oy of p of e minus conditional y times p of y conditional x, which is equal to sigma summing for ou of p of y conditional x times lambda of y, where the second line follows from the fact that y blocks the path between x and e minus. When the evidence nodes are set to a value, they initiate traffic and nodes continue updating until there is convergence. Perl in 1988 views this as a parallel machine where each node is implemented by a processor that works in parallel with others and exchanges information through lambda and pi messages with its parent and child. Trees, chains are restrictive because each node can have only a single parent and a single child, that is, a single cause and a single symptom. In a tree, each node may have several children, but all nodes, except the single root, have exactly one parent. The same belief propagation also applies here, with the difference from chains being that a node receives different lambda messages from its children. Lambda y of x, denoting the message x receives from its child y, and sends different pi messages to its children pi y of x, denoting the message x sends to its child y. Again, we divide possible evidence to two parts. E minus are nodes that are in the subtree rooted at the query node x, and E plus are evidence nodes elsewhere. See figure 16.12. Note that this second need not be an ancestor of x, but may also be in a subtree rooted at a sibling of x. The important point is that again x separates E plus and E minus so that we can write P of E plus E minus conditional x, which is equals to P of E plus conditional x times P of E minus conditional x, and hence have P of x conditional E, which is equals to alpha times pi of x times lambda of x, where again alpha is a normalized constant. Lambda of x is the evidence in the subtree rooted at x, and if x has two children y and z, as shown in figure 16.12, it can be calculated as lambda of x is defined as p of ex minus conditional x, which is equals to p of ey minus ez minus conditional x, which is equals to p of ey minus conditional x times p of ez minus conditional x, which is equals to lambda y of x times lambda z of x. In the general case, if x has m children, y, j starting with index 1, 2, 3 until n, then we multiply all their lambda values. Lambda of x is equals to pi of multiplying for all index j starting from 1 to m of lambda yj of x. Once x accumulates lambda evidence from its children's lambda messages, it propagates it up to its parent. Lambda x of u is equals to sigma summing for x of lambda of x times p of x conditional u. Similarly, and in the other direction, pi of x is the evidence elsewhere that is accumulated in the p of u conditional e plus and passed on to x as a lambda message. That is, pi of x is equals to p of x conditional ex plus equals to sigma summing for u of p of x conditional u times p of u conditional ex plus, which is equals to sigma summing for u of p of x conditional u times pi x of u. This calculated pi value is then propagated down to x children. Note that what y receives from x is what x receives from its parent u, and also from its other child z. Together they make up ey plus. See figure 16.12. That is, pi y of x is defined as p of x conditional ey plus, which is equals to P of x conditioning on EX plus and EZ minus. Which is equals to P of EZ minus conditioning on x and EX plus times P of x conditioning on EX plus divided by P of EZ minus, which is equals to P of EZ minus conditioning on x times P of x conditioning on EX plus divided by P of EZ minus, which is equals to alpha times lambda z of x times pi of x. Again, if y has not one sibling z, but a multiple, we need to take a product over all their lambda values. That is, pi yj of x is equals to alpha times pi multiplying for all this s not equals to j of lambda r s of x times pi of x. Polytrees. In the tree, a node has a single parent that is a single cause. In a polytree, a node may have multiple parents, but we require that the graph be singly connected, which means that there is a single chain between any two nodes. If we remove x, the graph will split into two components. This is necessary so that we can continue splitting EX into EX plus and EX minus, which are independent given x. See figure 16.13. If x has multiple parents ui, I equals to 1 to 3 until k, it receives pi messages from all of them. Pi x of ui, which it combines as follows. Pi of x equals defined as P of x conditional EX plus, which is equals to P of x EU1x plus EU2x plus and so on and until EUKX plus. That is, there will be k levels of summation, sigma for OU1, sigma for OU2, sigma for OU3 until sigma for OUK of the term. P of x conditioning on U1, U2, U3 until UK times P of U1 conditioning on E U1x to the plus times P of U2 conditioning on U2 x to the plus and so on until P of UK conditioning on E UKX to the plus, which is equals to again k levels of summation summing for all ui's of the term P of x conditioning on U1, U2, U3 and so on until UK times pi multiplying for all I starting from 1 to k of pi x of ui and passes it on to its several children yj, j equals to 1 to 3 until m. And the pi yj of x is equals to alpha times pi of, for those x not equals to j of lambda y x, lambda ys of x times pi of x. And in this case, when x has multiple parents, a lambda message x passes on to one of its parents ui combines not only the evidence x receives from its children, but also the pi messages x receives from its other parents u or r not equals to I. They together make up e u I x to the minus. So that is lambda x of ui is defined as P of EUI x minus conditional x, which is equals to doubling summation summing for all x and is summing for all u r net equals to I, where r is not equals to I, the index, of the probability P of EX minus EUR not equals to I plus, EUR not equals to IX plus, and also x, and also UR not equals to I, conditioning on UI, which is equals to doubling summation, summing for all x, and summing for all UR not equals to I of P of EX minus EUR not equals to I x plus, conditioning on x, and UR not equals to I and UI, times P of x and u are not equals to I conditioning on ui, which is equals to doubling summation, again summing for all x and summing for all u are not equals to I of P of EX minus conditional x times P of EU are not equals to IX plus conditional u are not equals to I times P of x conditional u are not equals to I and ui times P of u are not equals to I conditional ui, which is equals to doubling summation summing for all x and summing for all u are not equals to I of the term p of ex minus conditional x times p of u are not equals to I conditioning on u eu are not equals to ix plus times p of eu are not equals to ix plus divided by p of u are not equals to I times p of x conditional on u are not equals to I ui times p of u are not equals to I conditional on ui, which is equals to beta times, again, the doubling summations of the same term, summing for all x and summing for all u are not equals to I of the term p of ex minus conditional on x times p of u are not equals to I conditioning on e u are not equals to I x plus times p of x conditioning on u are not equals to I and ui. That is equals to beta times, again, the doubling summation of the term lambda of x times pi, where pi is for multiplying for all indexes are not equals to I of pi x of ur times p of x conditioning on u1, u2, u3 until uk, which is equals to the last line, beta times, right now there's no doubling sigma, it has been separated, where the outer sigma is summing for all x of the term lambda of x, and there's another inner sigma summing for all u are not equals to I of the term p of x conditioning on u1, u2, u3 until uk of the term pi, where multiplying for all r not equals to I of pi x of ur. As in the tree, to find its overall lambda, the parent multiplies the lambda messages it receives from its children. That is, lambda of x is equals to pi, where pi is for all index j starting from 1 to m of lambda yj of x. And in this case of multiple parents, we need to store and manipulate the conditional probability given all the parents, p of x conditional on u1, u2, u3 until uk, which is costly for large k. Approaches have been proposed to decrease the complexity from exponential in k to linear. For example, in a noisy OR gate, any of the parents is sufficient to cause the event and the likelihood does not decrease when a multiple parent events occur. If the probability that x happens when only cos ui happens is 1 minus qi, then p of x conditioning on u1 ui and not up, where p is not equals to j, is equals to 1 minus qi. The probability that x happens when a subset t of them occur is calculated as p of x conditioning on t equals to 1 minus pi multiplying for all ui in t of the term qi. And for example, let us say wet grass has two causes, rain and a sprinkler, where qr and qs is equal to 0.1. That is, both singly have a 90% probability of causing wet grass. Then p of w conditioning on r and not s is equal to 0.9, and p of w conditioning on r and s is equal to 0.99. Another possibility is to write the conditional probability has some function given a set of parameters, for example, as a linear model, p of x conditional on u1, u2, u3 until uk, w0, w1, w2, and so on until wk, which is equal to sigmoid of the function of parameters, sigma summing for index I starting from 1 to k of wi times ui plus w0, where sigmoid guarantees that the output is a probability between 0 and 1. During training, we can learn the parameters wi, I equals to 0, 1, 2, 3 until d, for example, to maximize the likelihood on a sample. Junction trees. If there is a loop, that is, if there is a cycle in the underlying undirected graph, for example, if the parents of x share a common ancestor, the algorithm we discussed earlier does not work. In such a case, there is more than one path on which to propagate evidence, and for example, while evaluating the probability at x, we cannot say that x separates E into EX plus and EX minus as causal upward and diagnostic downward evidence. Removing x does not split the graph into two. Conditioning them on x does not make them independent, and the two can interact through some other path not involving x. We can still use the same algorithm if we can convert the graph to a polytree. We define the click nodes that correspond to a set of original variables and connect them so that they form a tree. See figure 16.14. We can then run the same belief propagation algorithm with some modifications. This is the basic idea behind the junction tree algorithm. Lorentzen and Spielger-Holter in 1988, and also Jensen in 1996, and also Jordan in 2009.